Iríamos passar então agora ao Dr. Christopher Scott. Chris Scott, please.
Take up a statement. Yes, you may. Okay.
If you wish, you may leave.
Would you prefer to stay up here during the talks? Or?
O Dr. Chris Scott é professor associado da Universidade do Southern Maine. É doutorado na área do exercício, da fisiologia do exercício, onde é conhecido principalmente pela publicação de livros e artigos na área do dispêndio ou custo energético, principalmente nas atividades associadas à velocidade, à força e à potência muscular. Tem cerca de 50 artigos publicados em revistas indexadas com arbitragem científica, e foi durante alguns anos responsável pelo Departamento de Exercício, Saúde e Desporto na Universidade onde leciona. A sua conferência será sobre as questões associadas ao dispêndio energético no treino da força. Dr. Chris.
Olá, Portugal. Thank you very much for having me. I'm enjoying myself. I'm going to talk about the energy costs of resistance training, and we'll start off by showing you where I'm from. The United States, obviously. This area right here is the state of Maine, and my wife and I live right in this area right here. So that's where we traveled from to get here. Again, thank you for having me. All right. So when we talk about energy exchanges, the energy cost of something, these exchanges are best measured as heat. When energy undergoes conversion from one form to another, or energy transfer from one place to another, something is left over, a trace is left over in the environment, and that trace is heat. We can measure that heat, and that's what quantifies energy exchange. And so I'll start off with a story. This everyone recognizes as a steam engine. Steam engines, believe it or not, have been around for centuries. In fact, the first steam engine was actually devised by the ancient Greeks. It was actually a toy. It didn't look anything like this. But in the 1700s, they had locomotion engines, steam engines. Interestingly enough, while these things worked, nobody understood how they worked. And then right around the middle of the 19th century, about 1850, 5 or 6 scientists from different areas in the world came up with the science of thermodynamics that recognized how these things worked, how they essentially converted heat energy to forward momentum. This is a thermomechanical converter. It takes thermal energy and converts it to forward momentum. Now, make no mistake about this machine, the knowledge behind this, changed the world that we live in. It was called the Industrial Revolution. And from a scientific standpoint, any type of knowledge that changed the world we live in is applied to other areas of science. So from mechanical engineering, the physicists would apply this. Chemists applied this. Biology applied this. And early exercise physiologists applied it too. And they applied it to working skeletal muscle. And so we recognize that muscle gives off heat, and the more it works, the more heat it gives off. So therefore, like the steam engine, muscle must be a mechanical converter. And the way science works, the way progress is made, you don't prove things, you disprove them. And this man, by the name of A.V. Hill, he was called, a British exercise physiologist. He took a very primitive device that you see on the left here. This was called a thermopile, and it could actually measure heat production by a chemical reaction that took place in this chamber right here, where the arrow is. And he was given this instrument. It was very primitive, very crude, And over the years, he made modifications so that it became a very precise and a very valid scientific instrument. And he essentially changed it so that he could put a frog muscle, single frog muscle, in this chamber. Now, very importantly, this chamber had no oxygen in it. It was full of nitrogen, no oxygen. He would make the muscle give an electrical shock. One twitch would occur, and he essentially showed that in one twitch, he registered changes of 3/1000ths of a degree Celsius in 2/100ths of a second, which essentially disproved that muscle was a thermomechanical converter. It was not converting heat to mechanical motion. Something else was involved. And what he did was he looked at this frog muscle from a chemical standpoint, and he recognized that a certain amount of glucose that was in the muscle would disappear, and an equivalent or similar amount of lactic acid was formed. And so he recognized muscle not as a thermomechanical converter, but as a chemical converter device. So essentially the energy within the chemical bonds of this glucose to lactic acid conversion was what was responsible for muscle contraction. And of course, heat was also evolved in this. Heat. And this was, again, a very famous discovery, and he actually won the Nobel Prize for it. And so, unfortunately, it is very difficult to measure heat, especially in large organisms like ourselves. This is a direct calorimeter that was, I think they started to build this with experiments in 1895. And people, or a person, would live in this calorimeter for several days, and the amount of heat that it was given off was actually measured. And again, heat measurement determines what the energy costs of living were. And so we could determine from this device what the energy costs of living were. The device was modified about 7 years later, so about 1905 or so, they added gas exchange, where they were actually measuring the amount of oxygen that went in and the amount of carbon dioxide that was produced. And it is of interest that oxygen uptake measurement is actually a very simple thing to do. Measuring heat, very difficult. Measuring oxygen uptake is easy to do. And we recognized that the amount of heat that was produced was proportional to the amount of oxygen that was consumed. Okay, then that's how we started measuring oxygen uptake to estimate what the energy costs of living were. And I want to be very clear about this. We measure oxygen uptake. That's the measurement that we take, but we use it to estimate energy expenditure. And I have many colleagues who I'm very friendly with, but they don't understand the difference between a measurement and an estimate. When people ask me, what do you do for a living? I tell them, I estimate energy costs. I do not measure them. I guesstimate what an energy cost would be. So that's what oxygen uptake does. It allows us to estimate what the energy costs of living are. So let's go back to basics here, and let's look at oxygen uptake measurements and heat loss. We essentially burn in oxygen a glucose molecule here, carbohydrate, and this is a fat molecule. And I think everyone here is taught that the energy conversion for consuming 1 liter of oxygen, if glucose is the fuel, the conversion is 5 calories or 21.1 kilojoules. So that's the energy conversion, measurement, estimate of heat. For fat, it's 1 liter of oxygen representing 4.7 kcals or 19.6 kilojoules. I want you to focus on this number here. You're going to see it in several different slides. So now, I was a student. I was taught this. I memorized it and just took for granted. And as I got a little older, I started asking myself, 5 kcals is a little bit different than 4.7 kcals, or rather 21.1 kilojoules is different from 19.6 kilojoules. And I asked myself, why are they different? It's a 7% difference, and I want to know why. Why are they different? And so I started a journey to try to discover why this difference takes place. So where I found the answers best were in an area of combustion science. So there are actually scientists that are out there that actually study fire, combustion. And this is aerobic oxidation for a series of gases. This is, again, very old chemistry, if you will. A guy by the name of William Thornton in 1917. He recognized that for a given amount of atoms, this is per oxygen atoms, a specific amount of heat was produced. This can also be translated to the amount of electrons that are being exchanged from substrate to oxygen, and you can look at it in terms of moles of oxygen. Now, nobody in this room probably measures any of these things. What we do measure is liters of oxygen uptake. And essentially what this line shows us is a very specific relationship between the number of oxygen, or the amount of oxygen that's consumed, and the amount of heat that's produced. And the conversion is all aerobic, 19.6 kilojoules per liter of oxygen. So here we have our glucose again. Here's our fat molecules. These are our reactants. We're combining them with oxygen. The products that we have are carbon dioxide and water. And you'll note that the CO2 and H2O, the CO2 comes from glucose oxidation, and CO2 and H2O come from fat oxidation. So what's the difference if these are the same for glucose and fat? And if you look at the proportion of the types of chemical bonds in the molecule, you'll see that they're relatively consistent for glucose molecules. In particular, we're looking at this carbon-hydrogen bond here. There are 7 of them. It represents about 30% of that type of chemical bond within the glucose molecule. So this molecule essentially has an equal or a similar distribution of chemical bonds throughout. This molecule of fat, however, you'll notice that the greatest proportion of molecular bonds, carbon-hydrogen bonds, is 62%. So this molecule is primarily made up of one type of chemical bond. This is made up of several chemical bonds. And so if we were to actually look at what causes the variability, the difference between the conversion factors, it's really the proportion of bond types among molecules that determines what the energy cost differences will be. And so essentially, this is a chemistry type of a difference that we're looking at. So if I were to explain this based on Thornton's law, if you are a small molecule with many types of different chemical bonds throughout your being, if you will, you're going to be a dot that falls slightly off the line. If you are a long molecule with very similar bond types, you will be a dot that actually touches this line. Either way, you can see that it's a great relationship here. The scientists love straight lines, and that's definitely a straight line. So here's the conversion factor for aerobic. 1 liter of oxygen is 19.6 kilojoules. Again, this is for combustion. So we clearly do not undergo combustion when we perform exercise. So the question that I'm now asking is, how does combustion differ from the oxidation that occurs in mitochondria? So oxygen uptake and heat loss, remember combustion. Here's 1 liter of oxygen. Here's my conversion factor, 19.6 kilojoules for every liter. Here's my fat molecule. It undergoes breakdown in mitochondria, and it produces heat. Again, for every liter of oxygen consumed, 19.6 kilojoules of heat. Now let's look at glucose. Here's the conversion factor, slightly more energy per liter of oxygen uptake. Now let's look at the breakdown. Glucose, unlike fat, first undergoes anaerobic breakdown, no oxygen, okay? But heat is still being produced here. Then the lactate, or the pyruvate that's formed, undergoes mitochondrial respiration. That's the aerobic heat. So essentially what I'm showing you here is that there's an anaerobic component that produces heat, and there's an aerobic component that produces heat, And you add the both of these together, and you get 21.1 kilojoules. So here's the same thing in a figure format. So for those of you who like illustrations, here's my glucose molecule. Again, it contains an anaerobic and an aerobic component, and the conversion is 21.1 kilojoule per liter of oxygen. Here is my glucose molecule. Everything above this line is anaerobic. Everything below it is aerobic. This is glycolysis, anaerobic metabolism. We're forming about 2 ATP, which is about 7% of the total ATP that's formed. Here's my aerobic component, 34 ATP, about 94% of the total. So remember, with the aerobic conversion, we're getting everything below this line in terms of mitochondria at 19.6 kilojoules. And if I take the difference between 21.1 and 19.6, that tells me that the anaerobic component of glucose oxidation is about 1.5 kilojoules per liter of oxygen. Okay? This is my interpretation of oxygen uptake and energy cost conversions. So you might say to yourself, oh, that's very nice. Actually, I have a friend, very intelligent friend. He's a veterinarian, and he read some of my papers, and he said, Chris, this is very interesting, but how do you apply something like this? It's academically, it's great. You're a very intelligent guy, but how do you apply something like this? Well, it's actually very easy to apply this to the exercise sciences. Here is a typical illustration demonstrating for very brief, very intense activity. This is VO2 max right here. So we have a large anaerobic component. And I think everyone knows that when we exercise very intensely, anything that has to do with strength, speed, or power, the predominant fuel that's being used is glucose. And the conversion factor here is 1 liter of oxygen is 21.1 kilojoules. Then when exercise ends, we have a recovery oxygen component called the excess post-exercise oxygen consumption, better known as EPOC nowadays. And I use a conversion factor that is different than this. And what do we know about EPOC? What do we know about recovery? Well, we know recovery is pretty much all aerobic. We are burning a lot of fat and a lot of lactate as fuels during the recovery component. And what is the conversion factor for fat? It's different than this. What else do we know about recovery? Is there is no anaerobic component. So if I were to apply the slides that I demonstrated earlier, they will show you that the conversion factor is actually, for recovery, 19.6 kilojoules, because we're burning, again, there's no anaerobic component to the fuels that we're oxidizing in recovery. So I look at exercise and EPOC as actually very different in terms of the fuels that they are utilizing, and therefore the energy costs are going to be slightly different as well. And you might say to yourself, okay, Chris, that's very nice, but what does that mean to anybody who's walking around in the real world? Well, I will show you what it means. Here is our typical aerobic exercise model. Person at rest starts aerobic exercise, their oxygen consumption goes up, they exercise for 30 minutes, an hour, and then they stop exercising. The moment exercise stops, what happens to EPOC? It falls. Okay, one recovery period. Let's look now at an anaerobic type exercise, which we will call weightlifting, for example. So, this is data from our lab looking at several bouts of weightlifting. The lifting period itself was 15 seconds long, and that's what this black line is right here. A 15-second period involved 5 repetitions, I believe, and the weight was racked after it was all over, and this represents the recovery period. Okay? So we have, like the aerobic exercise, we have one exercise component in black, and we have one EPOC component. And right away, you'll see that there's a difference. Number one, the amount of time spent exercising is much less here, and the amount of time in recovery is much greater than it is during the exercise period. You'll also note that what we found with resistance exercise is that oxygen uptake actually peaks in recovery. Here, it peaks during the exercise and then falls in recovery. But this is an example of weight training. Nobody does one set of weightlifting. We do multiple sets of weightlifting. So here I'm going to add 1, 2, 3, and 4 sets. Here's 5, 6, 7 sets of exercise. Now, look what happens. This is what we do. This is what we've been trained to do. This used to be the exercise component. That used to be EPOC. Now, this no longer is EPOC. That's what we call the EPOC period. And what do? We take the oxygen consumption, the average oxygen consumption of oxygen going up and down. We take one average, and we look at the energy costs of anaerobic exercise, and we say, per minute, the amount of liters consumed represents the energy cost. And I look at this, and I say to myself, you know, I understand why the texts do this, but this I don't understand. Clearly, here's oxygen going up and down, and what do? We, in essence, force this aerobic exercise model onto the anaerobic model. So in other words, this is no longer anaerobic exercise. Where's my little red bar? See? Is everyone more comfortable now? This is what we do. Now, instead of saying this is anaerobic exercise, we follow the exact same model that we do down here. I decided several years ago that's not what I was going to do. So, during these recovery periods, how is this different? Well, if this is where we're going to be burning a lot of fat and a lot of lactate, look at all the recovery periods here. Look at the energy expenditure here, the amount of oxygen that's consumed. Clearly, the most amount of oxygen that's consumed during weightlifting is during the recovery periods. And if the recovery periods are when you're burning fat, this is probably the best type of exercise for weight control or body composition. That's the decision that I've come to anyway. There's not a lot of data to support this yet, but the evidence is slowly coming out that intermittent type exercise is actually better at body composition or weight loss, fat burning than the aerobic type exercise. All right, so enough of fuel utilization. Let's look at energy expenditure models. Let's look at steady state exercise. Let's look at non-steady state exercise, and we ask the question, particularly for ramping tests, are these two related? All right, so here's the aerobic way. This is low intensity steady state exercise. This is a series of very slow to moderately slow walking, and you'll recognize here's the workload, and in terms of meters per minute of walking speed, that represents the energy demand. Here's 6 different walking speeds. That's slower, that's faster. We can combine all of this data on one graph, and here's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You'll see it's a nice straight line. Walking speed, energy demand here, and what do? We draw a straight line, and we extrapolate this out. So instead of walking, we can now estimate what the energy expenditure is for jogging, running, sprinting. And to put it another way, the amount of oxygen that you consume is what and the energy expenditure is. That's the aerobic steady state model in a nutshell. All right, problem with this steady state model is that when we have low intensity exercise, oxygen uptake rises and then plateaus. With high intensity exercise, anything that involves strength, speed, or power, an interesting phenomenon takes place. And that is that the oxygen uptake, whoa, what are we doing here? Whoop. Whoop. All right, whoop. Up. Okay, so instead of a steady state plateau, what we get is a slow rise in oxygen uptake, and it will keep rising until you either fatigue or you reach VO2 max. So interesting phenomenon. Power output stays the same, oxygen uptake keeps rising. And because of that rise, we just don't know what the energy costs are for higher intensity exercise. And if I were to take this model here and plot this line on there, what happens is you reach a spot, which is the anaerobic threshold would be right around here. And what happens is oxygen uptake is now going to break off this linear line. And again, for strength, speed, and power, now we don't know what the energy costs are for any given speed. You know, for meters per minute, 200, it could be here, or it could be there. We just don't know. This is a significant problem. Okay, so let's look at ramp testing. Ramp testing is very unique. Instead of a steady state, what happens is you can get on a bicycle, and what happens is a computer takes over the increases in power output. But it can do so very slowly. And this is a paper that was written in 1994 by a guy named Carlin Wasserman. By the way, he was the guy that invented, if you will, the word anaerobic threshold. And he recognized that for any change in power output, there was a change in VO2. And look at the very linear line here. Scientists love straight lines, right? He found that there was a relatively constant relationship. And the amount of oxygen that was actually consumed was about 10.3 milliliters of oxygen per minute for every increase in watt. Very steady proportional relationship. But you'll also notice that this graph stops at about 150 watts. So this is low to moderately intense work. What happens, and I'm going to ask you, if we were to go to 200 watts or 300 watts or 400 watts, what happens? Does the line go straight, as we would like it to do, or does the line increase this way, as it does for steady state? Which is it? Anyone care to take a guess? Do you think it's a linear line, or do you think it goes upwards? Well, in reality, we don't know what the answer is. Another group of researchers came out and studied this phenomenon, and what they did was they looked at several different types of ramping. A slow ramp to exhaustion, medium ramp to exhaustion, and a fast ramp to exhaustion. What does that mean? It means that this is a slow ramp to exhaustion. This takes a typical person to exhaustion, 15 watts per minute. It'll take you about 15 to 20 minutes until you get to VO2 max. This is a fast ramp to exhaustion. You will achieve VO2 max in 5 minutes. That's how long the test takes. This is moderate ramping, so you will fatigue in about 10 to 12 minutes here. So what does oxygen uptake do with ramping? Here's the linear line. This is my anaerobic threshold. You'll see right up to the anaerobic threshold, there's actually no difference in oxygen uptake, just like Carlin Wasserman has said. But once you pass the anaerobic threshold, if you are going to do a very fast ramp to exhaustion, oxygen uptake does not stay linear. It does not rise. What does it do? It goes down. Completely different than what the steady state model says. So with this, we cannot determine at these high work rates, what would the oxygen uptake be for fast or slow ramping? And I look at this and I think to myself, you know, this might apply to weightlifting during these very fast, repetitions or sets are actually done fairly quickly. You're not over the course of 15 minutes or 20 minutes. They're much faster than that. So oxygen uptake can literally, depending on the type of test, go up or down. I can make oxygen uptake do whatever I want it to do, depending on the rate at which work is being performed. Okay, here is another study that was done with ramping, but this is with a treadmill. This is a guy, Jonathan Myers, he's at Stanford University. This is actually, it's not the oxygen uptake, it's the slope of the line. So it's you saw before with cycling, the line goes up like this, that's the slope of the line from the power output to the oxygen uptake. This represents the slope of the line. This represents a plateau. What this person was actually trying to do was determine if oxygen uptake plateaus during treadmill test to exhaustion. And you can see here, as the test proceeds, the oxygen uptake goes up, the slope goes up, then it plateaus, then it goes up again, then it plateaus again. And you'll notice as the longer the test lasts, the greater the variability. So oxygen uptake variability is now increasing, a lot like it did for this. Here, oxygen uptake is the same, and then it becomes very variable. Again, the same thing with treadmill testing. Here's my oxygen uptake. Again, that's the average straight line through there. So we have a lot of variability present. And the slope of this line represents an oxygen uptake change of about 3 to 3.8 milliliters of oxygen per kilogram body weight per minute. Okay, so this is my interpretation of the variability. Low variability, high variability. This is the intensity of the exercise. So for steady state exercise, down here we have essentially steady state where we have very low variability. And then I pass the anaerobic threshold and my oxygen uptake can become very variable. And this essentially represents the non-steady state during ramping. But even with this variability, I can still draw a measurement of central tendency or an average that will represent the energy expenditure regardless of the workload. So the point that I'm making here is we can estimate energy costs when work rates are changing very rapidly, but you're going to end up with a lot of variability. You need to understand there's a lot of variability in the measurement. Okay, another big problem. This is all I've talked about is oxygen uptake so far. We also understand that with heavy to severe exercise, there is after the anaerobic threshold, there's also an anaerobic component that we must start considering, especially for weightlifting. And as I'll show you, the variability is also there or apparent for anaerobic metabolism as well. All right, so several years ago, we were looking at the difference between cycling and treadmill exercise for a bout of exercise that lasted 1 minute, and it involved 250 watts of power output. So this is very easy to do on a cycle ergometer. We can just set the electrical ergometer at 250 watts and the person cycled for 1 minute. For the treadmill, I believe it was a 10% grade, and then the speed that person ran at was dependent on their body weight until we got up to 250 watts. 1 minute of exercise, and this is what we found based on oxygen uptake. For the cycle, we got 7.6 calories. For the treadmill, we got 9.9 calories. Now, most people only represent oxygen uptake measurements. So if I only reported the aerobic costs of this, the conclusion I would make here is that for the same amount of power output for cycling versus treadmill, treadmill would have a greater energy cost than cycling. And so we would probably go even further than that and say, oh, if you want to lose weight, don't bicycle, you must go on the treadmill because the greatest energy costs are here. We went one step further. We took lactate measurements, blood lactate measurements. I'll talk about those in a moment. Converted them to kcals, and you'll note here that 7.8 calories per cycle was higher than the 5.4 calories per treadmill. Again, these are statistically significant differences. What happens when, there's a lot of metabolic variability here. What happens when you add the two together? 7.6, 7.8, you get 15.4 total calories, energy cost, 9.9 plus 5.4, 15.3. You add the aerobic and the anaerobic together, what happens to my variability? Now it's no longer like this, now it's like this, much lower. So the variability is clearly decreasing here, and the energy costs are actually the same whether you bike or run on a treadmill with the same amount of power output over a minute's period of time. So my variability now has essentially been erased when I add the aerobic and the anaerobic costs together. Okay, here's another energy cost model. We've talked about steady state. We've talked about ramping. Let's talk about intermittent exercise. And we ask the question, again, are these all three related? So here is my typical model for steady state exercise. Rises at the start of exercise, steady state, and we have one recovery period known as EPOC. And you'll note that the majority of the oxygen uptake actually happens during the exercise period. And people still argue today, is this component meaningful? A lot of people would say in comparison with the amount of oxygen you consume during the exercise, it's not. Some people say that it is. So I'm just going to put, we don't know. But we, again, looked at weightlifting. And here's my model. And we did, or have done with the bench press exercise only. We've now looked at again, bench press with 1 set, and then we wrote another paper and did 2 sets, and then we wrote another paper and did 3 sets. And for all 3 conditions, we found that if you add up the 15-second exercise periods, exercise oxygen uptake was always the lowest amount of energy expended. Here again, it's the highest, here it's the lowest. And then if you were to separate these recovery periods and add them together, it always represented the greatest amount of energy expenditure. And so what we're showing here essentially is that during the exercise, here's the most amount of energy expenditure, here's the least amount, and recovery has the most amount. Completely different. And again, what's missing here? Come on. It's the anaerobic energy cost. What are they? All right. Here's a bout of work, 2 bouts of work in joules. Let's just say that these are repetitions for a specific weight training exercise. 10 repetitions, took 20 seconds to do this. Here's 20 repetitions, it took 40 seconds to do this. We have an aerobic component here and in white, and we have an anaerobic component here in black. And what we're going to do is we're going to add these 2 together to determine the total energy cost of this exercise. And notice now we're not measuring oxygen uptake as liters per minute, we're measuring it as liters. It's not a work rate, it's a work bout, is what we're talking about. So, the first exercise, the first papers that I wrote, we actually had a weightlifting bench where people were doing the bench press and then they'd rack the weight. We needed something a little bit more precise. And so I went over to in our university, we have an engineering department. I went over there and I said, I have a problem. I need to be able to measure or estimate what work actually is during weightlifting. And so I got a small grant and we bought a Smith machine. I think most people know what this is. The weight travels on this bar, and so it's only in vertical plane that we're lifting. The weight cannot go like this, and the weight cannot go like that. So I'm only in a vertical plane here. And these engineering people, they made this little pulley that here's a cable that travels along. The bar is counterbalanced. And as the bar goes up and down, the cable goes back and forth. And this little pulley device essentially measures the distance that the bar travels. And it gives us an output of what that distance is. And so we decided that we could probably get a good estimation of what work volume is by knowing how much the weight was on the bar, which is the force, and how much the distance that the bar actually traveled. And if you looked at the variability, the coefficient of variation, for one repetition versus another, the difference was only 25% of variability, a coefficient of variation. That's pretty accurate. And if you look at one set of maybe 10 reps to the second set of 10 reps, the variation goes up to about 0.74%. So we're below 1% coefficient of variation. So we have a fairly accurate way of measuring this work volume here. And so, excuse a lot of information here, but we'll go through this. This is one of the first exercise tests that we did on this machine. We chose the bench press simply because it's something that everyone likes to do. We chose a very low weight, 50% of 1 RM, and we did that because we wanted to avoid fatigue taking place, and we'll end up with that here. We just did one set. We had 7 repetitions, which took about 21 seconds, 14 repetitions, which took about 42 seconds, and 21 reps, which took about a minute. And we'll go over here to work, and this is the coefficient for the amount of work that was completed. And so essentially it's about 5%, which is actually very good. What this is telling me is the weight isn't changing, obviously, but the distance that these lifters are actually lifting the bar changes by about 5%, okay? People came to the lab, by the way. We had 8 subjects, and you think, oh, that's a low subject number, and it is. But we had each subject come in 3 times for each different lift. So we had essentially 9 data points for every subject and 72 lab visits overall. So the thing I want to point out here is you look at the aerobic energy costs. And remember, oxygen uptake, everyone accepts oxygen uptake. It is a valid measurement, right? Doesn't matter if it's a work rate, if it's a bout of exercise, regardless of what you're doing, you hook someone up to the metabolic cart, you measure the amount of oxygen they're consuming, and you say, aha, that's the energy cost. Well, we found out with a short bout of weightlifting, the coefficient of variation for the oxygen uptake was 47.4%. This is absolutely ridiculous, unacceptable. But again, most research that you see published, they only do one trial for each one of these. Here's my anaerobic. Now, nobody accepts anaerobic energy measurements, but it has the same ridiculous variability as the aerobic measurement. Look at my EPOCs, 30% or more coefficient of variation. Again, this is somewhat unacceptable, but watch what happens when I add the anaerobic component with the aerobic component plus the modified EPOC that I told you about earlier. The variation now goes down to about 21%. Still high, but it's starting to become a little more acceptable. What happens when the amount of time increases? So now instead of a short 20-second exercise bout, now I double that. Look what happens. My variation goes down, and when I add all three together, now I'm down to 15% variability. With a minute's worth of lifting, 21 reps, I add it all up, and again, 15% variability. So if I take the average of each one of these, 7, 14, and 21 repetitions, here's the amount of work that's done. This is my total energy cost. So this is aerobic and anaerobic. So here's the average of all my measurements. You can see here that the correlation for work, volume, and energy cost is actually pretty good. And so essentially what we have here now is if you take repeated measurements, not just one, but take multiple measurements, average them out, and you take multiple measurements of exercise, oxygen uptake, blood lactate, and that modified EPOC, and you have what looks to be a good relationship. But the problem that we have here, Victor, where are you? You know what the problem is, right? Does a good correlation prove cause and effect? No. So the truth of the matter is, if you ask me, is this model valid? I have to, as a scientist, if I don't want to have bias, I have to say, I do not know if this is valid or not. And that's the problem I have right now. It's looking good so far, but I don't know for sure if this is valid. Okay, so you can read all about it in a book that I wrote, and this is essentially the 3 components of exercise. And as I'll show you, I follow the old Margarita model to some extent. Here's my anaerobic energy expenditure. For every change in blood lactate from resting values, it's associated with a 3 millimeter per oxygen per kilogram increase, and that's the conversion factor using glucose here, or actually blood lactate. Here's my exercise oxygen uptake. Again, we're looking at strength, speed, and power, so we're using glucose as a fuel, glucose oxidation. And then the third measurement is I assume that only lactate and fat are being oxidized here, so my conversion factor is 19.6. And again, I obviously can't sit here and read out of the textbook, but if you're really interested in this stuff, I encourage you to buy my textbook so that I can buy a new pair of shoes. All right, this is Margarita's model in the 1960s. This has been, I think, I guess I would say invalidated nowadays. I think that's a mistake. I think this man was very clever and he was onto something, and it shouldn't be just disregarded what was happening. So I'm going to stay here for a few minutes and I'm going to show you what Margarita found. And essentially all you're looking at here is data for 2 subjects, okay? 2 subjects. One subject is physically active but is not an athlete. The other one is an elite athlete. So what he did is he had them come into his lab and he had them run at a steady state speed, okay, for a specific period of time, and then he would plot the oxygen uptake for that particular work rate. And so the steady, or the solid line here is essentially the sedentary person. On another day, he had them come in, run at another higher steady state speed. That's the oxygen uptake. On another day, higher speed right there. On another day, there's the oxygen uptake, and that was this person's VO2 max. But he didn't stop there. He kept going. He had a higher speed. Well, this person's already at VO2 max, and so oxygen uptake essentially plateaus. So here's the rate at which oxygen rises, and then there's VO2 max. Now the dotted line represents the athlete. So we had them run at the same speed as a sedentary person, and lo and behold, the slopes of these two lines are the same, about 3 to 3.8 milliliters of oxygen increase per minute of exercise, or the rate of exercise. Now this person is an athlete, so rather than it being at VO2 max, this person's oxygen uptake keeps rising until eventually they also reach a speed where VO2 max is. And you'll note now there's 3 lines we're looking at, 3 lines. Solid line here, dotted line over here, and then a dotted line up here. So you can see that 3 lines are represented here, and each one of them has the same increase in oxygen uptake per workload. Now, after exercise was completed, what he did was he took a sample of blood lactate, peak blood lactate, and then what he did was at VO2 max, he essentially and very cleverly matched the rise in lactate during recovery with the oxygen uptake during the exercise period. So if you'll note, solid line, this represents the sedentary individual. Here's VO2 max, and here is when the blood lactate starts contributing above VO2 max. And you'll note the slope of this line, the slope of this line, the slope of that line, and the slope of this line are the same. Then he took the athlete. Here's the athlete, VO2 max right there. That's when blood lactate, the way he looked at it, started to increase. And again, he matched it to the rate of increase with the sedentary person, the oxygen uptake. And he found that it was essentially identical to oxygen uptake. And so these are the numbers that represent the change in oxygen uptake with the change in blood lactate and the change in workload per minute. So he didn't stop there. He not only did work rates, but then he started doing work bouts. So this is runs on a treadmill at a 25% grade. This is a hell of a load. 20% grade, 15% grade, 10% grade. This it was 11 miles an hour. I don't know what that is in kilometers per hour, but that's a sprint. These people were sprinting. I mean, these are hellacious workloads. And you can see here that for a 25% grade sprinting at 11 miles an hour, the test had only lasted for about 2 or 3 seconds. Most people could only go about 5 seconds or so. But you'll notice that the slope of the line Anyway, the slope of the line here is 3.6, 3.55, 3.6, 3.6. Again, it's the same slope that he found for steady rate work. And then years later, DiPrampero and Ferretti, these are Italian exercise physiologists, they looked at running and they looked at swimming. And again, the slope of the line was very close to this increase in oxygen uptake per amount of blood lactate. So whether we're looking at work rates or work bouts, it appears that steady state increases in work output with energy costs are somewhat equivalent to intermittent type of exercise. So this is what I learned from Margarita. Again, this is the steady state model that I showed you earlier, but now instead of assuming aerobic metabolism for sprinting, running, weightlifting, I know that there's an anaerobic and an aerobic cost. And when I add them together, I'm going to get another straight line, which I will call a vector. And the vector represents the direction of the energy cost to work volume relationship, and it represents the number or the magnitude of metabolic systems that are involved. Here it's anaerobic and aerobic. So here's a question I'm going to be working on when the fall semester starts in my school. I've only done bench press so far, and I'm going to start looking at arm curl, leg press, and some other things. And a question I'm asking, do each one of these have their own vector, their own relationship, or is it the same for each one of these? I am praying that it's going to be the same for every exercise, because then it's going to be a simple thing to do. If every exercise you do has its own work volume to energy cost relationship, I'm going to have a headache for years. So, with the first hypothesis here, we have a single vector work volume energy cost, which essentially means that steady state, non-steady state, and intermittent exercise are essentially all the same if we were to look at the amount of work done or the rate at which work is done and the energy cost. But this isn't the only hypothesis. There's another one. Here, again, aerobic and anaerobic are complementary. I'm adding these two together. Again, it eliminates, or reduces, I should say, variability. But something else might be happening as well. We all know that as intensity gets more, the energy costs can change. And so here we might have, for example, for low to moderate intensity, an energy cost relationship that is represented by this line here. And then as exercise becomes moderately heavy to heavy, it might be an added cost. So you see the line jumps up. So there's another cost there. And then when we have severe exercise, that adds another cost. And that's our second hypothesis. And that means that essentially, the intensity, the higher you go, we have an added energy cost to each one of these. In that case, steady state exercise does not equal non-steady state exercise and does not equal intermittent exercise. So in looking at these two, if I put these together, I started wondering, how are we actually comparing these things? And if, for example, if you were to open up the American College of Sports Medicine book and try to figure out what the energy costs are for cycling or running, there is a formula that you would do, and it very much follows this linear line right here. And so if I were to, for example, look at the energy costs for cycling, for me, 75 watts, and for you, 75 watts, it would probably be about the same, because our weight is being supported by the bicycle seat, and we probably would have the same energy cost per amount of work that we're doing. But for any given subject, at some point, you're going to reach your anaerobic threshold. And what's going to happen to exercise? It's going to start going up. So this model might be good for between subjects, but within any given subject, this is typically the model that you would see, I think. So what did I do? I looked at the study where we did bench press 50% 1 RM, and I looked at this line. And then a couple years later, I did a study where instead of where we racked the weight before fatigue, we went all the way to fatigue. So I had two essentially data sets. And this is the work that was done. This is the total energy costs. The bottom line represents non-fatigue. So this is lifting, in which the work, load, and the energy costs had a very straight line, complementary, and we compared that to a data set where we actually lifted to fatigue. And when I first saw this, I couldn't believe what I was seeing, because what I was expecting was at some kind of a workload, you would start seeing it rising like this, like it does for steady state exercise. But no, that's not what we found. We found that with weightlifting, what happens is we get another complementary line that is parallel to the non-fatigue line. And if you look at the aerobic cost, the anaerobic cost, and the EPOC, or recovery cost, we found that regardless of the amount of work that was performed, now I figured this little thing out. My last slide, I figured this thing out. The aerobic during the exercise, okay, it adds, if you go to fatigue, for a given bout of bench press anyway, the aerobic increase in energy costs was about 0 to 1 calories. You add the anaerobic, or the lactate component, it was about another 1.7 calories. And if you add the recovery component, it was a constant of about 2.4 calories. So in other words, if you're lifting the same amount of work, if you're lifting the same amount of work, it looks like the amount or the increase in energy cost is relatively constant throughout the workload. So I explained this to Jose the other day. If you were to, Victor, let's imagine instead of this was work joules, let's say this was the amount of push-ups that you did. Let's say this was 10 push-ups, 20 push-ups, 30 push-ups, 40 push-ups, etc. Let's say I have an identical twin brother. We weigh exactly the same. He's a very, very strong guy. He can do 100 push-ups. Me, I can only do 10 push-ups. So I do 10 push-ups, and it's all I can do. I'm at fatigue. This is where I am for energy costs. He, on any given day, can do 100, but I ask him to do 10, that's his energy cost. Now, I train and train and train and train. Several weeks later, now I can do 20 push-ups. Well, he can already do 100. That's where he is. At 20, I am now fatigued. That's the additional energy cost. Okay? Hope I can do this. No more. I've had it. Thank you.
Thank you so much, Dr. Chris Scott. Please join me.
Want me to join you?
No, join me. O professor Chris Scott, como vocês tiveram a oportunidade de assistir, abordou a questão do dispêndio ou custo energético associado ao treino da força. Como ele frisou muito bem, isto é uma área extremamente recente, na medida em que esta problemática tem sido principalmente estudada no domínio da atividade física aeróbica. Salientou muito bem a diferença entre a avaliação do consumo de oxigênio e a estimação do custo energético, como também apresentou alguns argumentos que alguns poderão considerar provocatórios para defender a utilização do treino de força para efeitos de perda ou manutenção do peso. Obviamente, isto é claramente um conhecimento que merece ser pensado e repensado. Sendo assim, eu passaria então às perguntas que vocês quisessem colocar. Well, I have one question, if you don't mind.
No comment.
I noticed that you investigated mainly bench press at 50% of 1 REM. I don't know if you already investigated, but I would like your opinion on the effect of different intensities and movement speeds of strength training exercise on the energy cost and the EPOC.
Yeah, we haven't done. We pretty much we're at 50%. We haven't examined different percentages of 1 repetition maximum. Obviously, these represent studies that we just really started only 3 or 4 years ago. We're just adding sets to the same amount of exercise. But we have looked at the time of lifting. And we published a study that looked at lifting same amount of weight, same percentage of a 1 RM, I think it was 50%, and we looked at 1.5 seconds up, 1.5 seconds down, and we compared that to 4 seconds up, 1 second down, and 1 second up and 4 seconds down. Same amount of work. And what we found was that the longer you were involved in a work, so instead of a repetition lasting 3 seconds, if it lasted 5 seconds, the amount of energy cost was much greater for the longer the period of time that you lifted. But it did not differ in terms of a slow versus fast, concentric, eccentric workload. So we haven't done anything explosive yet, but this is just controlled lifting. And the conclusion that we came to is that if you really want to increase energy costs, it's probably be best that you would slow the weightlifting movement down a little bit. And that, it adds rather significantly to the overall cost.
Thank you.
Yep.
Mais questões? Dr. Hallam?
Chris, that was interesting. One of the things that we're doing, and I'm real curious if you've looked at it, we've been also looking at effort perception during cost, which is tightly linked at least during aerobic exercise, you see a nice correlation between effort perception and the metabolic costs of the activity during that aerobic ramped model. We haven't seen that clean relationship with effort perception, which many argue is linked then to compliance and whether or not somebody will continue to exercise. Have you looked at that? Because we're not seeing a clear relationship between effort perception. We're starting to look at this now in weight training, and we don't see that same relationship. Curious if you've looked at it.
Yeah, if the study that I just talked about, if you look at, we have to be very careful the way we set this up, because what do we know? We know that fatigue is going to add to the energy costs. So we have to be very careful right now that if we're going to examine weightlifting, and with different protocols, you can't add fatigue because that's going to add to the overall energy costs. But we did note that, I believe it was with the 1 second down and 4 seconds up, there was a greater perceived exertion than the 4 seconds down, 1 second up. And the alpha level actually changed. I mean, it was the same energy cost for both, but it was almost different for the perceived exertion that they thought was actually higher. So I think there is something there, for sure. I went to a conference as well, and Gary Hunter provided some information, and I was actually startled to look at, this is a guy who, he gets a lot of money for his studies and literally collects thousands of points of data, and just puts them through the statistical jumbotron type thing. And the number one factor for weight gain that he's found is perceived exertion. So the higher the perceived exertion for any type of activity, the greater the chance for weight gain. There's something there.
Yeah. Thank you.
Yep.
Mais alguma questão?
Thank you very much, Dr. Scott. I have a question. You showed us the energy cost of different type of activities and the variability of the aerobic and anaerobic component to the energy cost. And adding the two components, we have the same cost of the activity. But do you think that in special population like elderlies or athletes, since that they have a different body composition, so more muscle, more fast twitch muscles, do this proportion will change, or the between subject variability has an influence on the variability of the two components? So if we do an intermittent training, we probably should have to change all the parameters, the recovery and the intensity, in order to have the same effect stimulating different metabolisms.
Yeah, and it's a good question. I don't know the answer to that, but I do know, for example, that when we first started out, I won't call them special population of men versus women, okay? In order to keep your subject number high so you can get a paper published, you want as many subjects as possible. So we would add men and women together, and then very early on we realized that when you separate them out, the data are very, very different. So now we no longer do a pooled data, because we know that women and men are different in terms of that relationship between energy costs and work volume. Now you add the elderly on top of that, maybe that's a different population. You might be right. I don't know with athletes and so on and so forth, but my best guess from what we found, again, is if you only look at one energy cost component, let's say the aerobic part, you are going to get a much larger variability depending on how intense the workload is. That probably would also be true for someone who has more fast twitch versus more slow twitch muscle. But now you add the anaerobic component to that, and you might have, for example, a sprinter that does a certain amount of work and this much anaerobic and this much aerobic, but you add or compare that to a distance runner with lots of slow twitch muscle. They might have that much aerobic and that much anaerobic, and the mean value would maybe be identical for both of them. It's possible. But there, I've also seen data, you look at individual muscles twitching and so on and so forth, that fast twitch muscles cost more to do a specific energy cost. Whether that's true for the whole body or not, and whether we can actually see it, again, it's nice, and it gets me a little irritated when you look at, I call them the boys and girls of science and the hierarchy. That, I do blood lactate and I measure oxygen uptake, and that's okay. But, the boys and girls that take the muscle biopsy, they're better scientists than I am. But, as a point I showed, the variability in these measurements is so ridiculous that I think it's really meaningless unless you have all the components there. So if that answers or doesn't answer your question.
Thank you very much,
Yeah.
because it was a really interesting presentation.
Thank you.
With many informations and many questions to think about.
Yeah, as I tell my students, and in relation to what you just thought, we're scratching the surface here. I mean, I can easily do this until the day that I die, and who knows if we'll really uncover something worthwhile or not. But many different ways of looking at power output and reps and sets and percentage of 1 RM. And like I said, I am praying that the relationship is somewhat similar for across the different types of exercises.
Thank you.
Mais questões? Ora, não havendo mais questões, fazíamos então um intervalo de cerca de 20 minutos, um coffee break, sobre o qual depois retomaríamos os trabalhos.